Okay, so I guess I'm going to have to first spend a few minutes to introduce what's called ADS-CFT duality, or the anti-de Sitter conformal field theory correspondence. So, asymptotically, imagine you're all familiar with the notion of an asymptotically flat spacetime. So an asymptotically ADS spacetime, except if you want to be fastidious, people say asymptotically locally ADS, has a metric that near its so-called conformal boundary looks like this. So anti-de Sitter space goes off to infinity in spatial directions. And I'm going to be writing down what it looks like near spatial infinity. So in this coordinate, spatial infinity is at z equals 0. And then near spatial infinity, the metric is supposed to look like so. So for example, the ADS, beta, or black hole metrics that we looked at before have this general form. And V, well, there was or wasn't a mass term, but regardless, V was like r squared at infinity. And then you'll see that if you let Z be 1 over r, so Z equals 0 is r equals infinity. In terms of Z equals 1 over r, the black hole and ADS beta metrics both have this form. So they're typical examples of asymptotically ADS metrics. Of course, if ADS itself wasn't asymptotically ADS, something would be wrong with the terminology. But the black hole metric, asymptotically, is like the ADS metric because near r equals infinity, the mass-dependent term is subleading. Now, if we do have a metric like this, you see that, first of all, z equals 0 is not in the space-time. It's infinitely far away. Because the metric dz over z squared diverges, well, because the integral dz over z from anything to z equals 0 is infinity. In terms of r, it was even more obvious. R equals infinity was infinitely far away because the metric was dr squared, the usual one, asymptotically for large V. Sorry, wasn't quite true. V was r squared, so the metric was dr over r squared. Sorry, what I should have said was this. Either way, in terms of either z or r, we get a logarithmically divergent integral. So z equals infinity isn't in the space-time. It's called the conformal boundary. It's not a true boundary in the usual sense. And if we go back to the metric, you can ask what kind of structure the conformal boundary has. And the answer to that question is rather interesting. We can't just set z to 0 and get a metric on the conformal boundary because it would be infinite. There's a 1 over z squared. What we can do, naively, is to set z equals epsilon. Well, okay. We could make a Weyl transformation to remove this 1 over z squared factor. So it might look like the coefficient, you can ask this question, is the coefficient of 1 over z squared a metric on the conformal boundary? The metric being hij dxi dxj, or the line element being that. The answer is not quite, because the coordinate asymptotically locally ADS means that there is a function z that puts the metric in this form. But z isn't unique. You can transform z to e to the phi of the x's times z. Well, higher order means order z squared. And in the process, you also have to transform x by z-dependent terms. But the coordinate z that puts the boundary asymptotic form of the metric in this form is not unique. If you replace z by any e to the phi times z, where phi depends on all the other coordinates, and compensate with some higher order terms, the metric goes back into this form. This is only an asymptotic form, so, well, you ask that it should be true up to order 1 over z, but in fact you can do better than that. So the factor of z squared by which you would try to multiply to get a metric on the boundary isn't unique. You could instead use z e to the phi. And then the metric you'll get on the boundary will be e to the 2 phi times h. So what the boundary carries is not really a Riemannian metric, but only a conformal structure. In fact, that's the reason for the name conformal boundary. The conformal boundary has a conformal structure not a Riemannian metric. Conformal structure is defined to mean Riemannian metric up to Weyl rescaling so an asymptotically ADS manifold has not an ordinary boundary which would have a metric. It has a conformal boundary that has a conformal metric. Now, the way the ADS-FT correspondence goes let's say that you have a gravity theory with negative cosmological constant in dimension d equals little d plus 1. So the conformal boundary n will have dimension d. The correspondence tells us that to such a gravity theory there corresponds a d-dimensional conformal field theory. A conformal, or CFT, a conformal field theory is just a conformally invariant quantum field theory. It's a quantum field theory that can be defined with a conformal structure without requiring a Riemannian structure. The way the correspondence works is that you fix a conformal manifold n. You fix a d-dimensional manifold with a conformal structure. And the gravitational dual is given by doing the bulk gravity theory on all manifolds M with conformal boundary N. So on the conformal field theory side, you specify the manifold N with its conformal metric. And then in the gravitational dual, you allow all possible manifolds that are asymptotic to N, where the asymptopia has to involve the precise conformal structure that you specified on N. So what Hawking and Page did a long time ago with black hole thermodynamics with negative lambda was later reformulated as a special case of this procedure. So, in Hawking-Page, with lambda negative, n is chosen to be S2 times a circle, where S2 has a unit radius, and the circle has circumference beta, so I'll call it S1 beta. Then for fixed S1 beta, you study a conformal field theory on S1 on that n. So from the point of view of the boundary theory, you would be studying thermodynamics on thermodynamics on S2 at inverse temperature beta. So there is an interpretation as quantum field theory, or maybe I should say CFT thermodynamics, on the manifold S2 at temperature 1 over beta. So as one of the questioners asked this morning in objecting to my statement that the nature of the states that contribute to black hole thermodynamics was unclear, from a boundary point of view, it's completely clear. We're just doing ordinary thermodynamics of a standard type of quantum field theory, which is in favorable cases even known what quantum field theory it should be. In the bulk, though, we do quantum gravity on all m's of conformal boundary n. Now, quantum gravity is too hard in general, which also was an objection, I think, raised by another questioner. But in practice, or maybe by more than one questioner, but in practice, we study it for small g, and we do so by finding classical solutions. For small g, a classical solution will contribute very roughly e to the minus its action, and remember the action will be of order 1 over g, to the partition function. So, as g goes to 0, solutions with different actions, the one of lower action dominates over the one of higher action by an exponentially big factor. So one expects the dominant answer from the classical solution of least action. So in this particular setup where n is S2 times S1 beta, before the break we discussed the two classical solutions. One of them I called ADS beta. It corresponded to V being 1 plus R squared over B squared. And then there was the ADS black hole. V was 1 minus 2gm over R plus R squared over B squared. The first one allows any beta, so no matter what beta was, it's a possible classical solution with those boundary conditions. The second one, we have to, well, the number of values of m that gave a given beta was either 0 or 2, depending on beta. But in the case when there were 2, only one of them was good. So in some range of beta, for beta less than beta naught, this solution exists. And this one exists for any beta. Now we can make a quick test of whether these ideas work, and this kind of test was made in the early, well, you could argue it was done, this kind of test was done in the early days of ADS-CFT by reinterpreting what Hawking and Page had calculated. So before the break, we discussed some formulas for ADS black hole thermodynamics, but we didn't work out all the details. But if we'd worked out details, you see, first of all, T equals 1 over beta is the temperature in the boundary theory. So that's a statement of ADS-CFT duality, and that's an improvement on what Hawking and Page said. Hawking and Page had beta as a temperature-like parameter, but it wasn't the temperature measured by somebody who lives in the bulk, and I don't think they really had a good interpretation of it. The modern interpretation is that the quantum gravity theory with negative lambda is dual to an ordinary conformal field theory on the boundary, and the parameter that I called beta before the break is just the inverse temperature in that description. Now then, a fact about 2 plus 1 dimensional conformal field theory is that at high temperature, the entropy, high temperature for fixed volume, we're in fixed volume because we're on a two-sphere of unit radius. So high temperatures, fixed volume, the entropy goes like T squared and the energy goes like T cubed. In two space dimensions. In n space dimensions, the 2 and 3 would be replaced by n and n plus 1. So we didn't completely work out the black hole thermodynamics. I wrote down a bunch of formulas. But first of all, at high T, remember I said that at beta less than some beta 1, the black hole dominated. To show that, you have to compute the action of the black hole and also the action of the empty ADS beta solution. When you do, there's this Hawking-Page transition. At temperatures higher than that, the black hole dominates. So the black hole is believed to be completely stable, even non-perturbatively, for a sufficiently massive black hole, which means sufficiently high temperatures. And in that region, for the black hole at high temperatures, you do find this scaling with the temperature, as in the boundary CFT. So that's sort of an elementary test of this ADS-CFT correspondence that was made in the early days by reinterpreting formulas of Hawking and Page. Yes, I see a question.
Maybe I'm missing something, but are we giving a scale if we have a temperature in a CFT?
We're giving a scale because I said the spatial manifold was a sphere of unit radius. So we formulated it. When I say that the sphere has unit radius, I've given a scale.
Okay, so this CFT has an inherent energy scale inside in some way?
The manifold in which we formulated the CFT is a two-sphere of unit radius times time, which was periodic with imaginary period beta. When we have a two-sphere of unit radius, that's like saying that for a massless particle, the energy squared is roughly L times L plus 1 times 1, because the radius is 1. So the energy scale is set by the fact that the radius is 1. Okay. If you had given the sphere a radius r, then there would be powers of r in these formulas. If the radius is rho, there would be rho squared and rho cubed here.
Thank you.
Any other questions? I realize that in describing this negative cosmological constant story and telling you about ADS-CFT, I haven't been nearly as thorough as I was in everything else I explained, or at least that's the way it feels to me. And, well, anticipating that is why I was tempted to skip it completely. As I told you, the reason I explained it is I was hoping to get to the Ryu-Takanagi formula, and I wanted a clean conscience in invoking ADS-CFT at that point. But I might, in any case, fail to get to Ryu-Takanagi, in which case I will wish I had skipped this. Anyway, no more questions on negative cosmological constant? I know either at lunch or just before somebody asked the question I intended to answer after lunch, but I forgot what it was, so unless you ask again. Well, oh, the question is, can black, okay. So the question is, do black holes evaporate with negative cosmological constant? So remember, we had two branches of black holes. Beta as a function of R plus. First went up and then went down. So the small black hole, so there's a small black hole and a big one. Well, when the black hole is small, it's thermodynamically unstable, so it would like to evaporate. And in fact, it does evaporate. It evaporates to a thermal gas. But the evaporation can't be studied using the kind of methods we used in the asymptotically flat case, because the evaporation products go off to that very cold region at infinity and get reflected back. So it's not convenient. There's no convenient way to study it that's similar to what we did in the asymptotically flat case, but it is true that the small black hole evaporates. As for the big black hole, it's thermodynamically stable, so no, it doesn't evaporate. It's in equilibrium with the radiation around it. It's big, so it fills a lot of space. There's a big hole, so to speak. The conformal boundary is infinitely far away, but it behaves as if it's not that far away. So the entropy is mostly in the black hole, not the radiation. As I think I said maybe yesterday, there is perfect equilibrium between a black hole and radiation in anti-de Sitter space, in negative cosmological constant, if the black hole is heavy enough. And the branch where that's true is this big black hole branch, at least if you're above the Hawking-Page transition, which I think is a stronger condition than there's some Hawking-Page transition. In some region of the curve, the black hole is completely thermodynamically stable, so it doesn't evaporate. It keeps emitting and absorbing photons and gravitons, but on the average, it just sits there. And if it fluctuates to become a little bit too heavy or a little bit too light, then it will return back because its heat capacity is positive, so any fluctuation gets restored. So the small one will evaporate, but it's hard to study by the methods that we used in asymptotically flat case. The big one can be in perfect equilibrium with radiation, and that means it will be possible to make statements that go beyond leading order in Newton's constant. And I think we'll even make some such statements tomorrow. Any other questions? Okay, then we're going to move to net positive cosmological constant. But for positive cosmological constant, we're not going to discuss black holes. The reason is that with positive cosmological constant, you can have horizons even without a black hole, and that will keep us sufficiently busy. So the maximally symmetric space with positive cosmological constant is called de Sitter space. So in d dimensions, well, what did I do? Okay. We'll just do it in 4 dimensions. In 4 dimensions, the symmetry is SO5. SO41 in Lorentz signature. It'll be SO5 in Euclidean signature, which we'll get to in a bit. But starting in Lorentz signature, the metric can be written in a variety of ways, which exhibit different aspects of the geometry. There are actually more versions written in my lecture notes that I'm going to actually explain in the lectures for brevity. Here's one version of the metric. This is the metric of a 3-sphere a round three-sphere of unit radius. And t you could think of as a time coordinate. And as you can see, the radius of the sphere as a function of t is rho cosh t. So the three-sphere expands exponentially fast in both the future and the past. And the exponential expansion in the future is believed to be a good approximation to the present universe, or at least it's becoming a good approximation. And the universe then accelerates so fast that distant galaxies quickly become out of view. And therefore, if you just sit there like we're doing it here in the Milky Way, you have a cosmological horizon. You can't see beyond a certain distance. So that's captured by a Penrose diagram. In the Penrose diagram, as usual, you show only time and one spatial coordinate. And the spatial coordinate here you could think of as longitude on the sphere. So S3 has got a north pole, it's got a south pole, and in between there's a longitude. And for fixed longitude, there's a two-sphere, two angles that will suppress. So in the Penrose diagram, you show time and the longitude only. And the Penrose diagram looks like this. It's a square. Time runs vertically. So time infinity is in the top, time minus infinity is on the bottom. The North Pole and the South Pole are on the left and right. By N and S, I mean the North Pole or the South Pole of the sphere. So, as always, light rays that are fixed values of the angles that are suppressed, incoming and outgoing light rays, are at a pi/4 angle to the vertical, and they look like this. And the world line of an observer, so we're going to consider a geodesic observer, meaning an unaccelerated observer, an observer whose world line is a geodesic. Well, because of the symmetries, it doesn't matter which geodesic we pick. An example of a geodesic is an observer who sits forever on the North Pole. So in the Penrose diagram, this is the world line of our observer. And the picture immediately shows that this observer has past and future horizons. So because a light ray can't travel at more than a pi/4 angle in the vertical, so if it's not moving in angular directions, it travels in this picture in a pi/4 angle from the vertical. If it is moving in angular directions, then projected to this picture, the angle from the vertical is less than pi/4. But since you can't see at an angle more than pi/4 from the vertical, anything that the observer can see is to the past of this line. So this line is the future horizon. And similarly, you see, you can see something which is down here, but you can't influence it. To influence something, you send in a signal from the observer who wants to influence something sends in, for example, a laser beam that at most travels at no less than a pi/4 angle from the vertical. So it'll end in this upper triangle, and it can never get to the past of this past horizon. So the observer has a past horizon. It's a rather busy picture, so I want to redraw it. The region that the observer can both see and influence, this region is called a static patch. The reason for the name will be clear in a second, I guess. It's the region that the observer can both see and influence. So it's bounded by the future horizon, I'll just call it FH, and the past horizon, PH. And that region itself, I'll call curly P, P right. And then there's a complementary static patch that the observer can neither see nor influence, which I'll call P left. If you had another observer on the south pole, that guy would be here, since this is the south pole, the region that the observer could, on the south pole, could see and influence is the opposite static patch, P left. So the area, the horizon at any time is a two-sphere, and when I say horizon, it could be either the past or the future horizon. The horizon at any time is a two-sphere of radius rho, where rho is a parameter in the metric, which you hopefully remember here. So its area is 4 pi rho squared. So Gibbons and Hawking said, and this is only a couple of years after the original work on black hole thermodynamics, that again, A over 4G is an entropy that captures the observer's lack of knowledge of what's beyond the horizon. It captures the observer's ignorance. Now, in contrast to the black hole, here I really had to talk about an observer, because the horizon was defined relative to an observer and depended on the observer. In the special case of de Sitter space, because it has a lot of symmetry, all observers would see a horizon of the same area. By the way, when I said the area is the same at all time, I mean it doesn't matter if you capture it here, here, here. Any point on the diagram represents a two-sphere, because two angular directions have been suppressed in drawing the Penrose diagram. And any point in the diagram that's on one of the horizons is a two-sphere of the same radius. That's true because of the symmetries of de Sitter space. So anyway, Gibbons and Hawking said that also here, area over 4G is an entropy. And if you think black hole entropy is mysterious, let me assure you that entropy in the cosmological constant is entropy in the cosmological context is even less understood. So it's definitely more mysterious than black hole thermodynamics. But the fact that better established, so the entropy is rather mysterious, but that correlators in de Sitter space have a thermal interpretation. Is better understood. Apart from Gibbons and Hawking, the original references Figuri, Napi, and Hegkrone. Approximately 1975. So I will aim to explain to you how, in what sense, correlators in de Sitter space do have a thermal interpretation. And part of the reason for explaining it is that it will help us understand better the black hole also. Well, after we explain this, we'll see that we can understand the black hole better than what I've told you so far. So the way I've described the metric didn't show all the symmetries. But it did make some symmetries obvious. So an SO4 of rotation of the three sphere is obvious, but also time translations. generated by the vector field d by dt are obvious in this way. Sorry, what am I talking about? Sorry. Sorry. What I'm actually starting to say is wrong. So I want to make time translations obvious, but in this way to write the metric, they're not obvious. We can we can take that as a motivation to write the metric in another way. So I'll write the metric now in another way that exhibits all the symmetries. So we let x1, so this way to write the metric makes it obvious that it has the interpretation as an exponentially expanding universe toward the future or the past. And that's important in the real world because it's believed to be happening now to us. It does not, this way to write it does not make the full symmetries obvious. I will now rewrite the metric in a way that makes all the symmetries obvious. And in my lecture notes, but I think not in the lecture, there's a third way to write the metric that makes the analogy with the black hole in some ways more obvious. But I'll leave you to read about that. So we let x1 be rho sinh t, and for j bigger than 1, we let xj be rho cosh t times zj, where the sum from j equals 2 to 5 of zj squared is 1. So the z is parameterized a 3-sphere of radius 1, a unit 3-sphere. So these x's have been defined so that they obey minus x1 squared plus the sum of the others squared equals rho squared. So that makes obvious an SO41 symmetry. That way to write the metric does make it obvious that the space-time is a homogeneous space with SO14 symmetry. By the way, when I discussed anti-de Sitter space, I wrote the metric in a way that didn't make obvious the symmetry. Similar to this, there would be a different coordinate system that would make the symmetry obvious. So our observer orbit, so the observer, remember, is always at the North Pole. And I'll take the North Pole to be where Z2 is 1 and the others are 0. So the observer who sits always at Z2 equals 1, that's a particular point on the 3-sphere. That observer, well, with the right choice of the coordinates, is our geodesic observer who, in the other description, lives on the right boundary of the Penrose diagram. So with that choice, the observer orbit so that's our observer orbit in the manifestly symmetrical situation. And I hope you all recognize having seen these very similar formulas before, because we had them for the uniformly accelerated observer in Rindler space. So now we see that a Lorentz boost of the x1, x2 plane looks like rho d by d tau to the observer. And just so the formula is the same as Rindler space, but the interpretation is quite different. The observer is now sitting at rest in a geodesic. In Rindler space, the poor guy needed an infinite rocket engine so as to be able to accelerate indefinitely in the past and the future. So in Rindler space, it was a kind of mathematical model. Here it's a more realistic model. It's not that far different from what we're doing. We're more or less traveling on a geodesic in a de Sitter-like space because of the expansion of the cosmological acceleration. But you remember that the fact that the Rindler observer had an orbit that was an orbit of a Lorentz boost led to that person's observations having a thermal interpretation. And the same thing happens in de Sitter space. The de Sitter observer will make observations with a thermal interpretation. You can guess that as follows. You see the orbit is periodic and imaginary tau with period 2 pi rho, which I'll call beta ds, and is 1 over what's usually called the de Sitter temperature, TDS. So what we're going to find is that the correlations that the observer would measure by doing experiments along the observer's world line will be thermal at the de Sitter temperature. I probably should qualify this by saying that we'll be doing quantum field theory in a fixed de Sitter space. We won't try to address the questions of what happens when you allow Newton take into account gravity. What Gibbons and Hawking claimed is that when you have gravity, there's an interpretation in terms of entropy, not just thermal correlations. I will only be explaining the thermal correlation, interpretation of thermal correlations that you get for quantum field theory in de Sitter space as probed by this geodesic observer or any geodesic observer. Well, okay. So if I go back to this picture, we've now found the symmetry, namely boosts of the x1, x2 plane, which are generated by this differential operator in terms of the x's. We could call it K because K was the name we used before for a Lorentz boost generator. K moves the observer orbit forward in time. So K is rho d by d tau along the observer orbit. Since K is the symmetry of the observer's world line, it's automatically a symmetry of the region of space-time the observer can see and of the region the observer can influence. So K is automatically a symmetry of this static patch. Likewise, the same boost is a symmetry of the south pole, so it's a symmetry of the complementary static patch. And if you ask how that K acts, well, K on this picture in terms of the x's, K is x1 d by dx2 plus x2 d by dx1. It generates a boost of x1 and x2. But in the Penrose diagram, it moves forward in time in one static patch, backwards in time in the complementary static patch, and it's space-like in the future and past wedges. I hope you've seen that picture before, right? And the reason I've seen the picture before is that we were talking about a Lorentz boost of Rindler space, and here we have a Lorentz boost of de Sitter space, but the metric isn't the same, but the Lorentz boost is the same, so to speak. The important parts of the picture are the same. So everything we found in de Sitter space is going to have everything we found when we discussed Rindler space and the Unruh effect will have an analog for de Sitter space. So, okay. So roughly speaking, in any state, I need to explain something a little bit else first. So we'll continue to Euclidean signature. So we let x1 be minus I times x1e. And then all that does, as usual, is to flip a sign in the metric. Oh, don't tell me I forgot to write the metric in terms of the x's. Okay. The SO4-1 symmetry was obvious, but I didn't write the metric in terms of... So the Lorentz signature metric is the obvious one with SO4-1 symmetry. So having written that, now I can assert that in terms of the x's, the symmetry was manifest. And if I replace x1 by minus I x1e, we get the Euclidean metric, which is rho squared times plus dx1e squared. And now, again, the symmetry is obvious, but the symmetry is SO5. And the space is very familiar. The Euclidean version of de Sitter space is just a sphere. The sum of the x squareds being... So we had before the constraint minus x1 squared plus the sum of xj squared equals rho squared. In Euclidean signature, all that happens is we flip a sign. So now the manifold is a sphere. So you could ask, in terms of the sphere, what is the observer's orbit? So we had x1 equals rho cosh tau. Rho sinh tau. x2 equals rho cosh tau. There's 0. So now you have to let t be I tau e, x1 be I, or is it minus I x1e? And then what we get is just rho sine of tau e and rho times the cosine of tau e. That describes a great circle. That should not be a surprise. You hopefully know that on a sphere, a geodesic is a great circle. In Lorentz signature, we had an observer whose world line was a geodesic. When we continue to Euclidean signature, it's still a geodesic, but now a geodesic is a great circle. And the great circle, of course, has circumference 2 pi rho, which I called beta ds. And because the orbit in Euclidean, the fact that the orbit in Euclidean signature has circumference 2 pi rho is equivalent to the way I said it before, which was that from a Lorentz signature point of time, what I said before was that from a Lorentz signature point of view, the orbit was periodic in imaginary tau with period 2 pi rho. So this is just a more vivid way to say the same thing. Continued to Euclidean signature, the orbit of the observer becomes a circle with period 2 pi rho, the appropriate period of a great circle on this sphere of radius rho. So if we are considering correlation functions along the observer world line, that's the continuation to Lorentz signature. Well, let me just draw the sphere with a great circle in it. So here's the equator. Well, in 2 dimensions, the equator is a great circle. In 4 dimensions, the equator is a 3-sphere. It contains a lot of great circles. I can't draw a 4-sphere so easily on the page, but this circle is meant to be a particular great circle, right? So the Euclidean picture is that the observer is we're making observations along a great circle in the 4-sphere. Those observations are periodic in imaginary time. Periodic in Euclidean time. So when we continue them to Lorentz signature, we're going to get thermal correlation functions. The formal way to prove it would be to show that they satisfy what's called the KMS condition. So what the upshot is the following. In any state that is K invariant and continued from Euclidean signature, the observer will see thermal correlators at the de Sitter temperature. Those are the ingredients we need. We need K invariance, and we need the fact that our correlators come by analytic continuation from the Euclidean picture. So what I'll do next is to describe how to construct a state with the right properties. But I'll stop here for a moment for questions. Okay, I hope that doesn't mean you're all lost. Where are we going? Well, the goal is to show that correlation functions that the observer will measure have a thermal interpretation. And the reason to think so intuitively is that the observer's orbit was periodic in imaginary time. So to get a thermal interpretation, we need a state which is time translation invariance in the sense relevant to the observer, which means the state has to be invariant under the symmetry K. But we also need a state that can be interpreted in terms of analytic continuation from Euclidean space. If the state has those properties, then the correlators the observer measures, roughly speaking, will be periodic in imaginary time, so they'll be thermal. Any other questions?
I have one question. The observant dependence is it related only to the cosmological horizon and black hole horizon, or is also somehow related with describing the things with the Lorentzian signature and the Euclidean signature?
Well, first of all, any observer will see equivalent physics because de Sitter space has so much symmetry. Any two geodesics are equivalent by the symmetries. But what an observer, although the physics are equivalent, the regions of space-time different observers can see are different because the universe is expanding so fast that in the real world, distant galaxies are going beyond our horizon, assuming the acceleration continues. So different observers can see different portions of the universe, but any observer will experience past and future horizons. There's in quantum field theory in de Sitter space, I'm not making a statement about quantum gravity. I'm making a statement about quantum field theory in de Sitter space. There is a natural state, which I'll call psi ds, sometimes called the Bunch-Davies state. It's actually got a long history, and one of the important papers was by Bunch and Davies, so it's sometimes called the Bunch-Davies state. But I'll call this state psi ds. It has all the de Sitter symmetries. So in particular, it has SO1-4 symmetry. And it's defined by analytic continuation, or can be defined by analytic continuation from the Euclidean space, which in 4 dimensions means with the 4 sphere, because the 4 sphere is the Euclidean version of de Sitter space in 4 dimensions. So, in view of what I've told you, it will automatically be true that correlators on the observer's world line in this state psi ds will have thermal properties at the de Sitter temperature. It'll be true because the state has all the de Sitter symmetry, so in particular it has the symmetry K, and it's defined by analytic continuation from S4. So the fact that the observer's orbit is periodic in imaginary time means that the observer will see thermal correlators. So how do we define this state? As I kind of reviewed at the beginning today, just after the break, if you have any manifold on which you want to define a state, one way to define the state is to find a manifold of one dimension more whose boundary is the state you're interested in, and then a path integral on the big manifold, keeping fixed the boundary values on the small manifold, will give you a quantum state on the small manifold. So here we're going to do this with the manifold that I'll call well, I'll call this S. S will be S3. So I want to define a state of quantum fields on S3. And to do that, I will pick a manifold whose boundary is S3, and I'll do a path integral on that manifold with fixed boundary conditions. So my manifold is going to be a hemisphere. Which I'll call W. And so my state I'll call it psi prime W of phi s is an integral over the fields on W, restricted so that on S they agree with phi s, of e to the minus the action. I call that psi prime because it's not normalized. So the normalized version of the state will be the same thing divided by a normalization factor. And the normalization factor will be, of course, the inner product of psi prime W with itself. How would we compute the inner product of psi prime W with itself? Well, psi prime W was computed by a hemisphere path integral. So that would be our ket. And the bra we'd compute by another hemisphere path integral. And then we glue them together and integrate over the boundary values. And by the time we do that, we've just built up a four-sphere. So Z is the four-sphere partition function. So I defined a quantum state, and this description manifestly did define a quantum state. That's the good news. The bad news is that that description does not make it obvious that the quantum state has the de Sitter symmetries. In this presentation, the state has SO4 symmetry that rotates the hemisphere, but not SO5 symmetry that rotates the sphere in an arbitrary fashion. So I want to see SO5 symmetry. So now I'm going to define something that has manifest SO5 symmetry, but it won't be manifestly a quantum state. So we will then argue that the two are the same. So, see, I called this state psi prime W. So I'll formally define correlators in what I'll call psi prime ds as follows. So if P1 up to P little Pn are points in the sphere, then I just define these correlators by a path integral in the sphere. And so phi is a field on the whole force sphere. So literally, I just define these correlators by correlation functions on the force sphere with operator insertions wherever you want to make them. I've written this as if the operators are elementary fields, but the operators are really supposed to be arbitrary local operators, and that'll be important in a little bit. Now, this definition has manifest SO5 symmetry, and we can continue it to Lorentz signature time, and then we'll get manifest SO41 symmetry. In other words, if we take these functions and analytically continue them, we'll get SO41 symmetry because in Euclidean signature they have SO5 symmetry. But this is not obviously a quantum state, even though I wrote it as if it is. Correlators in a quantum state obey some inequalities. So O dagger O is positive in any quantum state, where O could be any product, or a product or sum of products of these phis. Right? No matter what O is, it's not local. It's any product of local operators or a sum of products of local operators or anything. In a quantum state, the expectation of O dagger O is positive. So here I define some functions, but I didn't prove to you that there are expectations of anything in a quantum state. In the other presentation, but here the symmetry was obvious. In the other presentation, it was obvious we had a quantum state, but the symmetry wasn't obvious. So what we want to do is to prove that the two definitions are equivalent. How are we going to do that? Well, first we consider a special case. All operators are in the equator, right? I have a force sphere, and the equator in a force sphere is the surface S equals S3. In my first definition of the state, where I defined the state by a path integral on the lower hemisphere, saying it that way, I was using the fact that S was the equator in the force sphere. So as a first special case, I consider all operators to be in the equator. So what I've called the expectation in phi prime ds well, whether the operators are in the equator or not, what I'm formally calling a correlation function in the state psi prime ds is the expectation of a product of operators computed on the sphere. But if the points happen to be in the equator, the picture looks like this. We're inserting a bunch of operators at points on the equator. Now, how do we compute the expectation of the same product in the state that I called psi prime w? Well, I take the cat represented by a path integral on the bottom half, then I take the bra represented. I'm doing something that causes this thing to jump. Okay. Then I take the cat is represented by a path integral on the bottom half. The bra is represented by a path integral on the top half. And I'm going to glue them together to compute a matrix element, except that now I'm supposed to make an operator insertion before the gluing. So now I insert operators on the hemisphere and then glue them. And then after the gluing, I've just gotten this picture on the left. So as long as the points are on the hemisphere, on the equator, it's manifest that the two sets of correlation functions are the same. I hope that's clear to everybody. Well, how are we going to get away from the equator? Well, I'm just going to use the fact that derivatives of local operators to finite order are still local operators. So the same reasoning gives us a slightly different, slightly more general statement that, well, first of all, I wrote it before as if the O's were elementary fields, but that was unnecessary. We have this relation for any local operators and points on the equator. And so P is, let's say, well, let U be a coordinate that vanishes on the equator. It's positive above and negative below. So, and then there's some other coordinates I'll call Y. So you could consider a point, a general point on the sphere labeled by Y and U. So if the P's are at U equals 0, then this statement holds. But we could replace O by any derivative with respect to U. What I want to do is to construct O of Y and U by summing the derivatives by a Taylor series expansion in U. The coefficients in that series are all local operators at U equals 0. So this identity remains true if the O's are replaced by derivatives of any finite order at U equals 0. So as long as we can get away with this Taylor series expansion, the restriction to U equals 0 isn't important. But we can get away with it because, well, in Lorentz signature, there's no singularity as long as the operators are outside each other's light cones. But in Euclidean signature, there's simply no singularity as long as the operators are at distinct points. So these series converge, so we can just compare the two. So we've learned, remember, one definition manifestly gave a quantum state. The other definition gave something that had all the de Sitter symmetries. And we've learned that the two are equivalent. Any questions about this? Yes?
Calculations. The easy thing is to put in the north and in the south pole the operators. Can we do something similar to bring them wherever we like?
Well, we can bring them wherever we like as long as we keep them away from each other because these series converge. But I can't tell you anything especially nice about the north or south pole. Any other questions? So we've learned that the state that has the symmetries, the state that manifestly is a quantum state also has the symmetries. So we've constructed a state with de Sitter symmetry. And we didn't normalize it, but the normalized version is just obtained by dividing by the square root of z, as I explained. Now, what I've just explained I view as kind of the main thing you have to know to understand de Sitter thermodynamics. And in Rindler space, this step was trivial. Why did I not have to make this argument in Rindler? I'm about to explain to you that once we know this, we can prove analogs of the things that we had in Rindler space. But in Rindler space, we didn't make an argument like this one. The reason was that in Minkowski space, the analog of psi ds is the vacuum. And the vacuum minimizes the energy. And you all kind of knew about it, so I didn't have to argue to you that it existed. And, well, many of you at least already knew that it can be generated by a path integral in the lower half space. And I didn't have to prove to you that the state generated by that path integral has Poincare symmetry, because you already knew that the vacuum has Poincare symmetry, and you knew that the vacuum was the state of lowest energy that would be generated by a path integral in the lower half plane. So I didn't have to go through a rigmarole like I've just done to construct a state that's both a state and also has symmetries. You knew most of it. I just had to remind you that a path integral in the lower half plane is a way to construct the vacuum state. So this state psi ds is the closest de Sitter space analog of omega, but it doesn't minimize anything. It's the most natural and nicest state, but it doesn't minimize anything. And therefore I couldn't define it as minimizing something. It doesn't minimize anything, because although it's invariant under all the de Sitter symmetries, none of them is positive definite. For example, we have that Lorentz boost K that goes forwards in time over here, but not elsewhere. And since it's not everywhere, future-directed time-like, it's not bounded below. And all the de Sitter generators, similarly, are not bounded below. So the state psi ds exists, but it doesn't minimize anything. So I could imitate this definition by saying that I compute it. Here I describe the vacuum by path integral on half of Euclidean space. For positive lambda, half of de Sitter space means a hemisphere. And then I could indeed define the state by a path integral on the hemisphere. But I did not have any shortcut to prove to you that it had the symmetries. The definition doesn't obviously have the symmetries. So when I discussed Rindler space, I took for granted some things you already knew that are not true in the same form for de Sitter space. That's why we had to go through this rigmarole to prove that there's a state that also has the symmetries. However, once we know that, we can just imitate the Rindler space arguments. So everything I said about Rindler space has a quick analog for de Sitter space once we know this. Which means there's one state that has all the properties you might want. So we just formally argue as follows. First, we take this sphere S. Well, okay. Let me explain the motivation. We have this Penrose diagram. And the equator was described by t equals 0, which also means that TE is 0. The equator is in the middle of the picture. And that's S. If I divide S into pieces, SL and SR, S left and S right, S right has for its domain of dependence the right static patch. S left has for its domain of dependence the left static patch. I may have forgotten to tell you the reason for the name static patch. With K regarded as a time translation generator for the observer on the North Pole or on the South Pole, if K is regarded as a time translation generator, these patches are time independent. So they're static from the observer's point of view. They're not static to anybody else's point of view. Every geodesic observer in de Sitter space has their own static patch. Anyway, what we want to do, so as in Rindler space, we want to construct density matrices rho L and rho R for the left or right static patches. And our setup is such that the reasoning we need to do this is exactly what it was in Rindler space. So, okay. So first of all, having a density matrix for the static patch is equivalent to having a density matrix for observations on its initial value surface, SL or SR, because of the fact that the static patches are the domains of dependences of the corresponding initial value surfaces. So let's think about it that way. So to construct the quantum state, now we're going to start where we started for Rindler space. To construct the quantum state on all of S, we do a path integral on the half plane, on the hemisphere W. That gives us the state psi prime ds. Then to get the corresponding unnormalized density operator, we would have a positive hemisphere path integral to compute the bra and a negative one to compute the ket. But if we want to take out, okay, I guess if I skip steps, it will become unclear. So we have a Hilbert space of all fields. As usual, we factorize it as H left tensor H right. These are fields on S left or on S right. So our state is in H, which is HL tensor HR. But we want to get the density matrix by tracing out H left. And also you have to divide by the partition function for normalization to make the trace 1. So apart from the factor of 1 over z, the density matrix is generated by a path integral on the whole sphere, except the sphere has a cut on S right. Remember, in Rindler space, we had a cut at positive x on half of time 0. Now time 0 is the sphere, and the cut is on half of time 0, the positive half. And the density matrix is a function of fields phi and phi prime just above and just below the cut. So the path integral on the whole sphere, but with a cut on half of the equator, and fixing the boundary values just above and just below, that path integral computes the density matrix for S right by the same reasoning as in de Sitter space, as in Rindler space. And once we understand that, you see, how can we build up the sphere with that cut? Well, we start with S right, and then we rotate S right inside the 4 sphere by an angle. What would happen if you rotated it by a general angle? You get something I have trouble drawing. Well, okay. Remember, in Rindler space, we had this half plane we rotated it by an angle theta, and we built out a wedge of opening angle theta. And we said that the path integral that did that was e to the minus theta times k right. So here we do the same thing. I can't draw the picture better than to do the same thing again. Schematically, I'm drawing S right as a half plane, and then I rotate it by an angle theta inside the sphere. The only real difference is that here this was in Euclidean space, so the wedge goes off to infinity. But here it's happening in a four sphere, so the wedge is compact. But it's again true that this path integral in this region would generate e to the minus theta k right. And if we set theta equals 2 pi, we get what we want, the sphere with a cut on S right. So we learned that up to a normalization factor, rho right is e to the minus 2 pi times k right. I actually forgot to say what k right was, but it's the same as it was in de Sitter space. We split k as k right minus k left, where k right acts on h right, k left acts on h left. So in this way, we learned that by exactly the same reasoning as in de Sitter space, we learned that the density matrix for observations in S right is thermal with k right as the Hamiltonian and inverse temperature 2 pi. The reasoning is really exactly the same once we know that the state given by path integral in hemisphere actually has the de Sitter symmetries, which, as I told you, the analogous fact in Rindler space was free because the state in question was the vacuum and you knew all about it. I didn't have to prove anything about it for you. So there are two main results. One is that rho right is thermal, and the second result is that the de Sitter state is the thermophile double state of the two patches, P left and P right. So remember, in Rindler space, the way we proved that statement was just to observe. See, once you know that rho is 1 over z times e to the minus 2 pi times k right. So the thermophile double state is just rho to the 1/2 regarded as a state rather than an operator. As an operator, it's 1 over the square root of z times e to the minus pi k right. And e to the minus pi k right rotates us through an angle pi in Euclidean signature. And just as in Rindler space, when you rotate S right through an angle pi, you just build up the lower hemisphere W. And the path integral on W, by definition, is the state psi ds up to the normalization factor. So I don't know whether you followed that or not, but what I've attempted to explain, once we know this fact, which basically tells us that the state constructed by a path integral on a hemisphere actually has the de Sitter symmetries, once we know that, everything we said about Rindler space has a precise analog and reaches the same conclusions that the state is thermal in the sense of k right of Hamiltonian, and that the natural de Sitter space state is the thermophile double state of the two static patches. Every important statement about Rindler space has a precise analog. I've said what I have to say about de Sitter space, and I think it's a good place to stop. So I'll stop for the day except for questions, but I will give you a small warning about tomorrow's lecture after you ask some questions. Well, if there are any questions. You're not required to ask questions.
I just wanted to confirm if I understand this correctly. The reason why the endless space discussion was simpler than this, does it have to do with the fact that we restricted the discussion to 1+1 dimensions?
No, had nothing to do with the dimension of space-time.
Okay.
The reason that Rindler space was simpler is that the analog of this statement is that the vacuum in Minkowski space is Poincare invariant. Well, two facts. It's Poincare invariant and has minimum energy. Because it has minimum energy, it can be computed by a path integral in a half space. Now, you knew those facts about the vacuum state in Minkowski space, so I didn't really prove them to you. In fact, I assumed you knew them completely, but following a suggestion, that last statement about the path integral in the half space I did explain at the beginning of today's lecture, but a lot of you at least would have known that too. Fundamentally, for Rindler space, you knew the things you needed to know. I didn't think most of you would know that the path integral on a hemisphere gives a state that actually has the de Sitter symmetries. So I had to prove that. Now, apart from the fact that I had to prove that, while the analog for Rindler space I assumed you already knew, all the rest of the arguments are exactly the same as they were in Rindler space. I possibly was less patient today than I was in when I discussed Rindler space. Also, the pictures are harder to draw because it's much easier to draw a wedge in a flat space than it is to convey in a picture the idea of a wedge in a sphere. And it wasn't clear to me whether I was drawing and explaining the pictures clearly enough that you understood them today. But the facts I proved about de Sitter space, or the de Sitter analogs of these facts, and the fact that assuming you already knew these facts is what, plus easier pictures to draw, is what made Rindler space easier. Any questions? More questions? Yes?
Could you compare, maybe again, the expressions for the entropy in de Sitter space and black hole? I mean, naively, they look similar. However, the systems are, of course, very different.
Mm-hmm. Well, I won't ultimately be able to do too much. Well, first of all, I'd like to say I explained my point of view about it a year ago in Hamburg, the last time I was here. But I can't repeat it this week because this week we're doing more basic things. And we wouldn't really have time to get in that direction. I'm not totally sure how complete or convincing that picture was anyway. But fundamentally, regardless of what I said or didn't say a year ago, the de Sitter case is much less understood than the black hole case. I can tell you what Gibbons and Hawking said in about 1975. They said that the partition function, meaning the path integral on S4, well, usually a thermal partition function we interpret as the exponential of entropy minus energy times temperature. Oh, sorry, minus beta, energy times inverse temperature. But they said that in de Sitter space, because it's a closed universe, there's no conserved energy. So they said that in the case of de Sitter space, the partition function should just be e to the s. And semi-classically, the partition function is just the exponential of minus the action. So their point of view was that the action for de Sitter space is, the entropy of de Sitter space is minus the action. They have no microscopic definition at all of in what sense that's an entropy. But anyway, this was their proposal. Now the computation okay. First of all, there's no boundary, so the action doesn't need a boundary term. And for an Einstein manifold, this is just a constant times the volume. Well, constant over G, let's say, times the volume, times lambda, I guess. So computing the volume of the force sphere, you get a formula for the area, sorry, for the entropy, which they showed was A over 4G. Actually, if you follow the derivation I gave this morning, a la Karlip and Teitelbaum, you can prove that the action is equal to A over 4G without calculating either the action or A. In other words, that reasoning shows that the action is A over, minus the action is A over 4G. But this sheds no light on the sense in which minus the action is an entropy. And it's far less understood than the black hole case. Even far less well established in the black hole case. There are some fun things to say, but I kind of had my turn to say them last time I was in Hamburg, and I wasn't planning to go in that direction this time. So I can refer you to my papers. Any other? I'm sorry not to be more forthcoming than that.
I'm having another question.
Maybe I'll say one thing about this, one fun thing about de Sitter space. You know that as the universe exponentially expands, it becomes empty, because galaxies that are not bound to each other recede beyond the cosmological horizon. But even galaxies, the stars eventually merge, or they collapse to black holes. The black holes evaporate. The elementary particles leave. So in the far future, every static patch is empty. And therefore, Bousseau argued on purely thermodynamic grounds that since the static patch spontaneously evolves to be empty, the second law of thermodynamics must be telling us that the empty static patch has maximum entropy. And what I actually did a year ago, last time I was in Hamburg, was to give a definition of entropy such that it was true that the empty static patch had maximum entropy. But I'm not going to repeat that seminar here. Other questions?
Yes, I had another question. Okay, sorry. Do you hear me?
Yes?
Yeah. So I was wondering, now that we saw the analogy between the Rindler wedge or the Rindler spacetime and the Sitter,
Yes.
is there a deeper understanding or meaning why there's no analogy to anti-de Sitter space?
Well, tomorrow I will explain that it's actually a threefold analogy. There's Rindler space, de Sitter space, and the black hole. They're perfectly analogous. So we're going to redo the black hole tomorrow, first thing, and exhibit the analogy between the three. And in discussing the black hole there, it will not be very important if the cosmological constant is 0 or negative. So we could do the negative case, but we could equally well do. The negative case has the advantage that it's well defined beyond low orders. The 0 cosmological case is unstable in higher orders. But otherwise, it will not matter if the cosmological constant is 0 or negative. I said I would give you a warning about tomorrow's lecture, and this is as good a time as any to give it. So there's this perfect threefold analogy between the three cases. And what I will do at the beginning tomorrow is to explain the third leg of the analogy, being the black hole. And if you want to understand black hole thermodynamics, it's really important to understand that case. I feel that today's explanation of de Sitter space was probably not as clear to most of you as the explanation was of Rindler space. Possibly I was less patient with the explanations. It definitely was more complicated because I had to prove something which we got for free in the Rindler case. And finally, the pictures were harder to draw. Plus, you might be understandably tired after about 6 hours of lectures. So because of all those factors, I suspect that today was less clear than it was when I explained Rindler space. However, I will begin tomorrow with the story for the black hole, which is exactly analogous to what we did today for de Sitter space. And just as today, the main thing we had to prove was this. And otherwise, everything else was a formal argument. There will be exactly the analogous statement tomorrow, which will be the main statement, except I won't prove it or I won't say more than a couple sentences because the proof is the same as it was today. So I think you'll be confused in tomorrow's lecture if you don't understand what I've told you today. And in case this explanation wasn't completely clear, I think you'll be much happier tomorrow if you've at least read the section of my lecture notes that I just tried to explain on de Sitter space. It's near the end of section 6. And, well, I'd like to believe it's very clearly written in a way that was hard to make equally clear in a lecture, unfortunately. So anyway, that's my advice about tomorrow's lecture. I don't know if there's more questions or if we
Yeah,
should call it
there's
down.
one question.
Yes, okay.
On following on the same note of the very important result and the proof. It just stems from my lack of understanding of Euclidean correlation functions. So I just want to understand how we stated the existence of the psi ds. So we said that we started with Euclidean correlation functions, which are manifestly SO5 invariant.
Yes.
Then you can do analytical continuation, that's good. And then we just say this must correspond to some correlation function of some quantum state,
Well,
which we call it to be psi ds. Is that
no.
how we define psi ds?
Well, to begin, it was just notation. So
Okay.
I defined this symbol to be the path integral or the continuation.
Okay, so that's the definition of psi ds.
Well, it's the definition of what this symbol means.
okay,
But from that point of view, it's not obvious that this is the definition of a quantum state.
right.
Because for a quantum state, the correlator should have some positivity. So how are we going to prove the positivity? The most natural way to prove the positivity is to find a definition of a quantum state that agrees with this. So then, what we did, the path integral in a hemisphere manifestly defines a quantum state. But it's not obvious that that quantum state has the de Sitter symmetries. So
Got
the
it.
main step in the proof was to show that expectation values in the quantum state defined by the hemisphere path integral actually are simply the four-sphere correlation functions.
Thank you.
Sure.
I wanted to ask about the manifold that you said that we needed to define in the states. Also, you said that we need that the manifold has the rank S, and then we can compute our path integral in that manifold. Is invariant also which manifold that we use as long as it has the same rank. And and my second question is that manifold, what do we need? Also, we just need it to have an Euclidean metric, or we need it to have also, for example, to be differentiable or some cohomology?
Well, any manifold, let's, to keep things simple, let's be in Euclidean signature. So our manifold has a Euclidean metric. Let it be smooth, or at least smooth enough that the quantum field theory makes sense. Then any W gives some psi W, which will be in the same Hilbert space associated only to the boundary. But that state in general won't have nice properties that we might want. Here I wanted the state to have the de Sitter symmetries. And there's no W that made that manifest, so it needed an argument. But to have it true, W really had to be the hemisphere. For that particular choice of W, it's true that the state has the de Sitter symmetries. Any W will give some state, but it won't give the state we want. We wanted a natural state with de Sitter symmetries. What we wanted was a state with de Sitter symmetries that can be defined by analytic continuation from Euclidean signature. Because those are the properties we needed for thermality, right? So for this particular case that W is a hemisphere, we were able to argue that the state has de Sitter symmetries and satisfies the fact that, that what we define by that symbol actually are correlation functions in the state.
So you said that psi de Sitter, this state, is not a vacuum state. But if there is a vacuum state at all for the case of de Sitter.
Well, I'm not certain what you mean by the phrase vacuum state. What the state I called psi ds is the closest de Sitter space analog of the vacuum state in Minkowski space. It doesn't minimize anything, but there's nothing you could minimize because none of the de Sitter generators are bounded below. So if there's anything that deserves to be called the vacuum state in de Sitter space, this is it. By the way, the fact that any state spontaneously evolves to this one is an example of its vacuum-like properties. Okay, maybe we're finished. Oh, no, not quite.
So I have a question that I was wondering for a long time. I mean, does all of this, the entropy that we are talking about, has a direct analogy, for example, to a classical communication system? So can we, in a way, or a quantum, let's say, a system where a communication, let's say in a quantum level, that has a von Neumann entropy, but is there like a system that could resemble this kind of structure, a boundary of or interaction of the system? Do you think?
It's a little hard to make, I mean, that question would need to be a little bit more specific for me to be very helpful, I'm afraid. But I would like to tell you that as one goes deeper into black hole thermodynamics, and I will not be able to give you tomorrow more than a few hints at best, more and more deep ideas of information theory become relevant. So that is part of what I meant when I said on the first evening that Einstein's theory knows more than it should about the quantum theory that it's a limit of.
Maybe one more question from Zoom. There's the question whether you can say anything about uniqueness of the de Sitter symmetric.
Of the de Sitter state?
Yes.
Well, it's not the unique state that has the de Sitter symmetries. It's just the simplest one. It is unique. Well, it's unique the way I defined it, by the fact that excitation values in this state are given by Euclidean correlation functions. And I imagine it's unique. I imagine it has uniquely the following property, that the Euclidean correlation functions have no singularities except where 2 points meet. Although that might be untrue, sorry. Okay, I was winging it, I'm afraid. It's the nicest state, but I'm not sure I want to say too much about the senses in which it's unique. Anyway, see you tomorrow at 10:30, I think, or is it 11? At 11, okay. Yeah, well, I'll see you at 10:30 for coffee if you choose to come early.